The primary purpose of VoIP is for making phone calls. In order for people to speak with each other over a VoIP trunk, their speech must be digitally encoded, transmitted across an IP network, and then converted back into a form the human ear can interpret. In this module, we'll see just how this is done. In general, VoIP protocols manage call signaling and media negotiation. This means that they handle setting up and tearing down phone calls, as well as coordinating what audio format will be used for the media. VoIP protocols don't generally handle the audio themselves, they just set up the pathway for two endpoints to send and receive media in agreed upon formats. The audio formats used with voice over IP are generally called codecs, which is short for coder-decoder. Asterisk supports numerous audio and video codecs, each of which is implemented in its own codec module. Humans speak by vibrating air to create analog sound waves. Sound waves can't be reliably and rapidly transmitted over great distances, so for IP telephony, they must be converted to a digital representation that describes the original sound. There are many different ways to digitally represent audio, and each approach is defined by its own codec. Each codec has several distinguishing features. The sampling rate, or the number of audio snapshots taken per second, is one important factor. Historically, 8,000 Hz, or samples per second, has been the rule. Over the past several years, higher quality wide-band codecs with sampling rates of 16,000 or even 32,000 Hz have become increasingly common for VoIP calls. A codec may also specify how many milliseconds of audio it puts into each packet to transmit. Most codecs used for IP telephony use 20 or 30 millisecond packets, though some codecs are configurable. Two of the most important features of any codec are its complexity and its bandwidth consumption. They're mentioned together because they're often inversely related. The more complex a codec is, the more computational power it requires to translate audio to or from that format. More computational power means longer delay when translating audio and fewer simultaneous calls per processor. However, more complex encoding algorithms often compress audio more efficiently so that each frame uses less of your disk or network capacity. In VoIP, there are different media streams for transmitted and received audio. The simplest and most common digital format will use 64 kilobits of bandwidth for each stream. And that 64 kilobits is just for the audio. The IP and UDP frame headers add another 16 kilobits or so of bandwidth in each direction. Highly compressed codecs use under 10 kilobits of bandwidth for the media stream, but are often more complex to encode or decode and may have lower audio fidelity. Some codecs also bear a fee for use. When deciding which codec to use on a particular channel, you'll usually want to balance among the audio quality, bandwidth usage, and translation cost. In order for a VoIP call to work, both endpoints need to agree on what codec will be used for the channel. Remember that a typical call consists of at least two channels in asterisk, one channel from the calling phone to asterisk, and another channel from asterisk to the dialed phone. The same codec does not necessarily have to be used for both channels, as long as asterisk supports the codec on both channels. If this is the case, asterisk will transcode the audio, meaning that it will convert from one audio format to another. This is very useful, but it has a cost in terms of processing overhead and latency. It's often preferable to avoid transcoding, but there are several circumstances where there's no choice. To see a matrix of transcoding delays for each of the codec combinations your asterisk system supports, run core show translation on the asterisk console. Asterisk has native support for many common audio codecs. We'll compare and contrast a few of these here. G.711 is the most ubiquitous in the telephone world because it was the first widely supported codec and is still in use on the PSTN. The two variants of G.711, MuLaw and A-Law, are very similar. MuLaw is the default in North America, and A-Law is the default for Europe and most of the rest of the world. It is a simple, uncompressed codec that uses a lot of bandwidth but gives decent audio quality. It's free to use, and it is the forefather of many other audio codecs. Almost all VoIP devices support G.711. GSM is very popular with asterisk because it offers a balance between audio quality and bandwidth, and is available for use at no charge. Its quality is slightly less than G.711, but many people can't distinguish the two, and GSM uses only 13 kilobits of bandwidth instead of G.711's 64 kilobits. It's relatively easy to transcode to or from GSM. G.729A is another codec that is popular with asterisk. At 8 kilobits of bandwidth, it's even more compact than GSM and offers slightly better sound quality. This is achieved through a sophisticated compression algorithm. Better compression means less bandwidth is required, but it also means that transcoding is more resource intensive. Another fact to consider is that G.729 is not free for commercial use. License fees for its use are usually included in VoIP phones, but separate licenses must be purchased from Digium to transcode to or from G.729 in asterisk. You can visit the product page for the G.729 licenses Digium offers by following the link in the Attachments tab of this presentation. There are several variants of G.729. It's worth knowing that Digium's implementation supports only G.729A and not G.729B or other variants. If you're using this codec and experiencing any problems with audio quality issues or with getting calls to connect, make sure that the device you're using is set to use only G.729A. This often means disabling a feature that may be called comfort noise, CNG, or silent suppression. The last codec in our list is G.722. Each of the several G.722 variants have great audio quality because they sample at 16,000 Hz, twice the rate of any other codec listed. The higher quality is especially noticeable on audio conferences. It uses quite a bit of bandwidth, but for some applications it's worth it to enjoy the better audio. G.722 doesn't yet enjoy wide support on VoIP devices, though more and more vendors are adding support for it into their products. Every VoIP call uses a codec. If everything is working properly, most users won't know or care what codec they're using, but as an administrator, it's important to know what codecs your Asterisk system uses. You should be particularly aware of the impact VoIP calls have on your network, and how your Asterisk system handles the transcoding that you request of it. There's not a good rule of thumb for how many simultaneous calls a given network will support, or how many simultaneous transcodes a given Asterisk system is capable of. In general, you should try to use the codecs that consume the least amount of bandwidth while providing acceptable audio quality, and you should minimize transcoding when you can. It's not feasible for most Asterisk systems, but if you can standardize on a single codec for all the devices and trunks Asterisk connects to, it may be worth doing so. If you will have to transcode, make sure that your system, especially the processor and memory, can support the number of simultaneous transcoded calls that you expect. In this module, we've explained that a codec is a specifically formatted digital representation of audio. There are many different characteristics that define each codec. Asterisk supports numerous audio and video codecs. Asterisk is most scalable if it doesn't have to transcode among multiple codecs, but it can transcode if necessary. We'll move on now to discuss device naming conventions in Asterisk.